And here we go. So let's start with the history part of the lesson, which is the beginnings of quantum physics. So the first person, hold on, I'm having an issue with the share. Try it one more time. Here we go. All right, we're good now. So the first person that we need to look at is this guy named James Clerk Maxwell, who was a Scottish physicist. And in 1865, he basically came up with this new idea that says, okay, light is an electromagnetic wave. So at some point in history, we didn't know what light was. We just kind of looked at it. But he predicted and stated that light is an electromagnetic wave. And people didn't really know what that was at the time. So it was a big deal that he came up with this idea. Now, let me show you what an electromagnetic wave looks like. It's basically an oscillating, so like a constantly changing electric field traveling along some direction, and then a perpendicular, constantly changing oscillating magnetic field. So they're kind of together and they're traveling off in some direction. So as you can see from this graph, it's in 3 dimensions, X, Y, and Z. So it's going off in the Z direction, and the electric field is going up and down on the X direction, and then the magnetic field is going side to side on the Y direction. But they're oscillating together perpendicular to each other. So this is a revolutionary idea at the time. However, this was still considered classical physics. So we needed another person to come in and expand upon this idea. By the way, this was only a prediction, a theory. So we didn't really have any proof of this at the time. Okay, so that was Maxwell. Now we have another guy named Heinrich Hertz, who in Germany in the year 1887 did an extremely important experiment that proved the existence of the electromagnetic waves. So he basically went out and showed that these things exist, therefore in proving Maxwell's theory. And as you guys know, throughout all of your years in school, one of the basic things about science that we learn about is the scientific method. You have some theory or some hypothesis, and the only way to show that it works or that it is something that exists is through experiments. So Maxwell came up with the theory, the hypothesis, and Heinrich Hertz came up with the experiment that basically put it all together. Now, this experiment that Hertz did is what eventually led to the beginning of radio communication. So without Hertz, we wouldn't be able to be having this conversation right now, because we're all having this conversation because of Wi-Fi, and Wi-Fi is a form of radio communication. Okay. Now, another thing that Hertz did around that time in another experiment was that he observed that a charged metal object will basically lose some charge when it's exposed to light. And that's kind of like a weird thing. You imagine you have like a piece of metal and you shine some light on it, right? Let's say that the piece of metal has some charge. You shine some light and then you measure its charge again and it's somehow less. But all you did was shine light on it. So he observed this effect, and it's now known as the photoelectric effect. However, what he observed in the photoelectric effect is not something that was able to be explained at the time. So that was the contribution of Hertz. Now let's look at the next person. In the year 1900, you had a guy named Max Planck in Germany who was concerned with this problem known as the black body radiation problem. Now, this is extremely complicated, but let me give you like a basic way that the black body radiation problem works. So at the time, scientists knew that all things radiated some type of energy from them, right, in the form of heat. So think about like when you go to the kitchen and you turn on your stove, right? And you turn the coil onto high and you look at it, as that thing starts to get hot, it changes color, right? It starts to glow red. And that's when you know it's really, really hot. In fact, that thing is so hot, it's probably like 900 to 1,000 degrees Fahrenheit. But even before that thing starts to glow, it's giving off radiation. It's just radiation that we can't really see. So the problem was stated that, okay, how does the intensity of the radiation by some black body, and the black body is something that absorbs all of the radiation that goes onto it and releases it at certain wavelengths. So how does the intensity of the radiation that it emits depend on the frequency of the radiation that is let off and the temperature of the body itself? How are those things related? Now, some other scientists at the time were coming up with this idea that, okay, as you make something hotter and hotter and hotter, it starts to glow different colors. So think about somebody working with metal, right? They're blacksmithing, say like making metal tools, like making a sword or something like that, right? The hotter that thing gets, the more like white it starts to glow, right? And white being the hottest possible temperature. However, based on observations, all of the things give off all kinds of radiation. So it could be ultraviolet, it could be infrared, and only a small piece of it is actually visible to us. So this graph that I'm showing you right now shows the color of a glowing object depending on its temperature. This is something that was observed. So if you heat something up to about 3,000 Kelvin, right? About 5,000 degrees Fahrenheit, it will glow red. If you bring up that temperature to 4,000 Kelvin, about 7,000 degrees Fahrenheit, it'll start to glow green. And if you bring it up even higher to 5,000 Kelvin, 8,500 degrees Fahrenheit approximately, it will glow blue. And if you make it hotter and hotter and hotter, it will eventually go off into a type of radiation that we can't see, off into the ultraviolet and above. Similarly, on the other end, if it gets cooler than 3,000, it'll go down into the infrared, which we cannot see either. Well, this was what was observed. However, there was no math at the time that correctly predicted this for different objects. So they didn't really understand what was going on, is what I'm trying to tell you guys. But the classical physics that we knew at the time predicted that the intensity of the radiation will increase up to infinity. But that completely disagreed with what was observed. In comes Max Planck and comes up with this really different and revolutionary idea at the time, that the only way for this to work is that the energy that's given off by or absorbed by that thing that's radiating can only be whole number multiples of some quantum of energy. Looks like I spelled quantum wrong. Let me fix that real quick. Quantum. So quantum meaning like a single count of it. So let me erase that real quick. So he came up with this formula, E equals HF. So it has to be some multiple number of that HF, where H is some constant and F is the frequency. Now, through experiments, he was able to figure out the value of that number H, that constant, but he really couldn't explain why that was true. Like, why was this happening? Basically, he did it by luck. He did some math tricks and made the formula fit the curves that I just showed you before, those radiation curves. But the thing that was revolutionary about this is that this assumption was allowed Planck to correctly derive the formula that fit those experimental results. But I'm not going to bother you guys with the math because it's really hard math, and it's we don't need to worry about it. Anyway, so that's where Planck stepped in. Now, the next person, and the last one that I want to talk to you about, is the one that brought all of these ideas together, which was, of course, the famous, probably the most famous physicist of all time, Albert Einstein, who in 1905 in Germany came up with 3 ideas that completely changed physics as we know it. Now, going back to the experiment that Hertz did about the photoelectric effect, Albert Einstein was able to correctly explain what happened there. This explanation is what won him the 1921 Nobel Prize in Physics. But in that same year, he developed the idea of special relativity, which is the very famous equation E equals mc squared, and explained something known as Brownian motion, which is, not to make it too complicated, but basically gave strong evidence that atoms were something that really existed. So he came up with the photoelectric effect explanation, E equals mc squared, and basically proved the existence of atoms all in the same year. So it's very, very impressive stuff that Einstein did. It's no surprise that he's considered the best of all time. So let me give a quick explanation of the photoelectric effect and how the experiment worked. So we have this circuit here, right? We have a voltage source V down at the bottom that is variable, meaning that we could change it, make it higher or lower. Over at the top, we have a glass tube with a metal plate that's positively charged and an electrode that is negatively charged. Now, if you look at the signs of this thing, notice that over here, we got plus and minus. And over here, we have minus and plus. Since those two guys are reversed, it's going to completely cancel out whatever current is generated by the battery. So you should expect to see over here where it says A, 0 current. Okay. But this is the interesting thing that happens with the photoelectric effect. We shine some light onto the glass tube, onto that big positively charged plate. What ends up happening is that some electrons are released from that plate and sent over to the other side. Now, if you look at the negatively charged electrode, they should be repelled because the electrons are, of course, negatively charged as well. But they are coming in so fast that some of them get through anyway. And then they are able to form a current, which is then read over on the other side on the ammeter. And as the frequency of that incoming light is increased, the current of in the circuit also increases. So that's kind of giving us a strong implication that as you increase the frequency, you're letting go more and more electrons, giving you a higher current. Now, the classical model at the time, hold on, let me erase this one. According to Maxwell, is that if we were to increase the intensity of light, meaning if we were to make the light brighter, the energy, the kinetic energy of those released electrons would increase. But the experimental results were something completely different. It showed that the intensity of light had nothing to do with any of this. The only thing that changed the energy was the frequency of the light. And that was something that was very puzzling to the scientists at the time. They didn't really understand why that was. But Einstein came up with this idea. By the way, this is a graph of the kinetic energy versus the light frequency. From this experimental result, we see a linear relationship between the kinetic energy and the frequency of the light. And the slope had a value of a very, very small 6.63 10 to the minus 34 joules second. So to explain this, Einstein went ahead and said, okay, he said light is basically composed of little particles or packets of energy, which he ended up calling photons. And these photons were released one by one, basically a quantum or a single piece of it. Each quantum of light has an energy of hf, which is the exact same equation that Planck had proposed 5 years earlier. So this idea gave a good, concise, clear, and simple explanation of what Planck predicted. Now, this is very strange because up until that time, people only believed light to be waves. But Einstein proved that light also behaves as particles. And there are several experiments that you could do and look at with your own eyes the way that waves behave as both particles and as waves. So this equation, E equals hf, is extremely important because this equation is what started the entire idea of quantum physics. All right. So this equation is known as, hold on, I gotta go all the way down here to take this one off, as the Planck-Einstein relation. As you can see, sorry, my screen froze. Okay, E equals hf is the Planck-Einstein relation. Sorry about that, guys. As you can see, it's a very simple formula. The math is not difficult at all. So this H number, one that was proposed by Planck, is called the Planck constant. And it is 6.63 10 to the negative 34 joules second. So this number came from the slope of that graph that I showed you a little while ago. The linear relationship between the kinetic energy of the released electrons in the photoelectric effect versus the frequency of the incoming light gives you a nice slope of 6.63 10 to the negative 34. And as you can see, it's a very tiny number. And this constant is crucial and critical to the study of quantum physics. Okay, so let's look at a little bit deeper into this relationship. One of the formulas, of course, is E equals hf, but if you do not know the frequency and you only know the wavelength of the light, you could still calculate its energy because we know that the frequency is c over lambda, or c over the wavelength. So another way of calculating the energy would be hc over wavelength. Again, c being the speed of light. Now, we're dealing with extremely small amounts of energy. So at the time, there was an emerging field in physics known as nuclear, atomic, and particle physics. And they came up with this new unit of energy to to basically make it a little bit easier to calculate the energy. All right, it's called an electron volt. The definition of the electron volt is the amount of energy that is required to accelerate one electron across 1 volt of potential difference. Now, we got to take it way back to like January in class when we were talking about potential and potential energy for electric charges. The way that we get the value, the number value of the electron volt, is by looking at E equals QV. E equals charge times voltage. So if our voltage is 1 and our charge is 1 elementary charge, then it's 1.602 10 to negative 19 coulombs times 1 volt, which is 1.602 10 to the negative 19 joules. Again, we're dealing with tiny amounts of energy, so rather than write out 10, that big number, 10 to the negative 19, you can just write 1 EV. It makes it a little bit easier. Now, with that in mind, we could also express Planck's constant in terms of electron volts. So again, the Planck constant is 6.63 10 to the negative 34. And as you can see, I divided it by the amount of energy that is equivalent of 1 electron volt. I canceled out joules. And I end up with this number at 4.14 10 to the negative 15 electron volt seconds. So if you're given a problem, right, that is explicitly dealing with electron volts, you would use this version of the constant. Hold on, let me get a color here. You would use this version of the constant instead of the other one. So if you're dealing with joules, you use the first one. If you're dealing with electron volts, you use the second one. Let's look at some examples of how to use the Planck-Einstein relation. Example 1, let me give myself some lines. Okay, it says here, at the peak of the sun's radiation spectrum, each photon carries an energy of about 2.7 electron volts. What is the frequency of this light? Now, here's what we know. Hold on a second. Here is what we know. We know that the energy is 2.7 eV. We want to figure out the frequency of the light. So we got to use the formula E equals HF. Now, F ends up being E divided by H. So we're going to divide 2.7 EV. And then we're going to, we're going to plug in 2.7 EV and then divide by the Planck constant. Now, again, we have two versions of the Planck constant, one in joules and one in electron volts. Since the unit that we're dealing with is electron volt, we have to use the electron volt version, which is 4.14 10 to the negative 15 EV seconds. The electron volts cancel out. So if I divide 2.7 with 4.14, I get about 0.65, rounding down to 2 sig figs. And then we could take this frequency, this scientific notation and bring it to the top, make it 10 to the 15. And this would be hertz. 6.5, 10 to the 14 hertz. Now, just to make another additional comment here, this frequency, 6.5 10 to the 14, is on the visible part of the spectrum. So this is visible light. And Give me 1 second. I'm trying to look at my table, the one that I gave you guys the other day. This is visible light, which is going to be the color of this light would be kind of like yellow, no, blue-ish green, somewhere between blue and green. All right, based on that frequency number. In fact, it's more blue than anything. All right. Now, of course, that wasn't asked, but you know, if you're curious, you could still compare it to that table that I gave you guys and see what type of frequency, what type of radiation it is, and what color it could be if it's visible. Okay, let's look at another one. This one says a quantum of hard X-ray radiation carries 2.0 kilo electron volts of energy. And what is its wavelength? Okay, so here's what we know. We know that the energy is 2.0 keV. By the way, kilo is 1,000 of something, so this would be 2.0 10 to the 3 electron volts. We want to figure out its wavelength. Now, the equation that we got to use here is hc over wavelength. So the wavelength here would be, what we got to do is basically multiply both sides by the wavelength and then divide both sides by the energy. Over on the right-hand side, wavelength cancels out. And over on the left-hand side, the energy cancels out, and then you are left with this formula for the wavelength. Wavelength equals hc over E. Now, H again is 4.14. Hold on, let me make a mistake there. 14 times 10 to the negative 15 eV seconds. C is 3 times 10 to the 8 meters per second. So your seconds here cancel out. And we're dividing by 2.0 10 to the 3 electron volts. Electron volts cancel out too. Okay. So the unit that's left over is meters, which is, of course, the unit of wavelength. Now, when I multiply 4.14 times 3, I get 12.42. 10 to the negative 15 times 10 to the 8 gives me 10 to the negative 7. We're still got to divide by the 2.0, 10 to the 3. And this would be meters. Finally, what we got to do is divide 12.42 with 2. And we end up with about 6.2, right? We're rounding for the proper number of significant figures. And then the scientific notation, -7 minus 3 minus 10 meters. And there's your answer. Okay. Now, of course, if you had a scientific calculator, like a good one, or if you use Desmos like we use all year, you could just plug all of this in exactly like you would write it on your piece of paper or whatever you're using to do your work and get an answer right away. That's totally fine. But if you want to do it the old school way, that's how you do it. So to summarize everything that we talked about, give you a history lesson about the early parts of quantum physics, dealing with 4 main people: James Clerk Maxwell, Heinrich Hertz, Max Planck, and Albert Einstein. So when I give you an assignment later, I'll give you some questions dealing with these 4 men. And then finally, we did the Planck-Einstein relation, E equals HF, the Planck-Einstein relation. Where H is 6.63 10 to the negative 34 joules seconds, or H equals 4.14 10 to the negative 15 electron volts seconds. And we talked about the electron volt, which is 1.602 10 to the negative 19 joules, if you need to convert. Also, from here, we want it in terms of wavelength, we could do that too. These are 2 equivalent expressions. So yeah, that's the full summary of what we just talked about. I have a recording of this. I will have a recording of this, and I do have the recording of the other video, and I'll post both of those guys up to YouTube at some point today. I will let you guys know when there's an assignment for this. It will probably be up today, but if it's not, it will be up tomorrow. I'm gonna leave a due date open. I'm gonna put a due date in the gradebook, but there will not be a late penalty for any of that. So just be on the lookout for those announcements. And yeah, that's basically it for me today. So thank you again, as always, for making the time to listen to me talk about this stuff with you guys. It means a lot to me, so I appreciate it. And yeah, I'll talk to you guys next week. Have a great weekend, everyone. All right? See you guys later.
Bye.
Bye.